Hello everyone. Today we are going to discuss potential gradient. So in order to understand potential gradient, let us consider two parallel plates and let the upper plate be positively charged and the lower plate be negatively charged, and let us assume charge on the plates be equal in magnitude but opposite in sign, so that electric field is directed from positive plate towards negative plate and the electric field is uniform, okay, in the region between the plates. Now let us consider test charge plus Q naught, okay. So I'm taking test charge plus Q naught inside the electric field. Now if the charge is moving from A to B, okay, that is along the direction of electric field, okay, then what we find is that I'm writing if the motion of charge plus Q naught is along the direction of electric field, okay, then the field, that is electric field, does positive work, okay, it does positive work on the charge. So this is to be noted, okay. Now let's consider this case, okay. So we are having two plates and the upper plate is containing positive charge and lower plate is containing equal amount of negative charge, so that the electric field in the region between the plates is uniform. Now let us consider test charge plus Q naught, which is moving opposite to the direction of electric field, that is it is moving from point B to A opposite to the direction of electric field. Now I'm writing if the motion of charge plus Q naught is opposite to electric field, okay, then the field, that is electric field, does negative work on the charge. So we have this. So we need to understand these two concepts in order to understand potential gradient. Now I'm erasing this, okay. And we know electric field equals force per unit test charge, okay. So we are taking test charge plus Q naught, okay. So therefore we can write electric force equals Q naught times electric field. So this is electric force. So we have this. Now electric force experienced by plus Q naught is acting in downward direction, okay. So this is the direction for electric force experienced by charged particle plus Q naught at point A. Let's say at point A. We are starting from A, okay. So A is the initial point and B is the final point, okay, inside the electric field. Now work done in moving or let me write in this way, work done by electric field in moving test charge plus Q naught from point A to B is. So work done in moving from A to B. So we can write in this way, okay? We know small work done equals force dot displacement, and if we integrate this, then we get total work done equals integration force dot displacement. So we use this concept, okay? So we have integration, okay, from A to B, okay, clear? So we have this, and electric force, it is given by this expression, dot displacement, clear? So dl is the displacement, okay? So we have this. Now we can write this expression in this way, integration from A to B, okay, and electric force equals Q naught times electric field dot displacement. So work done in moving from A to B equals Q naught. I am taking Q naught out of the integral sign. So integration from A to B, E, that is electric field dot displacement. So we have this. Now dividing both sides of above equation by Q naught, we can write work done in moving from A to B divided by Q naught equals integration from A to B electric field dot displacement. Let us call it equation 1. Okay. Now we know from the definition of potential difference, okay, work done in moving test charge from A to B, okay. So we can write in this way, work done per unit charge or per unit test charge in moving it from A to B equals potential at A minus potential at B. So this is from the definition of potential difference, okay, and this difference is called potential difference between point A and B. So we have work done per unit positive test charge, okay, that is Q naught in moving it from A to B equals VA, that is electric potential at point A, minus VB, that is electric potential at point B, or potential difference between point A and B. So this is equation 2, okay. Now from, so let me change the color, okay. Now from 1 and 2, okay, we can write VA minus VB equals integration from A to B E dot dl. So we have this, okay. So we have this. Now if we come into this expression, okay, then what we find? We find VA minus VB and work done in moving positive test charge from A to B, okay, are independent of the path, that is we can bring test charge plus Q naught. Okay, so I'm drawing in this way. We can bring trace charge plus Q naught from A to B following any path. We can have this path, or we can have this path, okay, or we can have any path. So for convenience, I'm taking a straight path from A to B. So we need to understand this, okay. So V A minus VB and W, that is work done in moving positive phase charge from A to B, are independent of the path. So we need to know this, okay. So I'm erasing this, okay. Now let us call it equation 3, okay. Now if we look into equation 3, okay, on right hand side, then if the integral, so I'm writing in this way, okay, integration from A to B, E dot dl is positive, then electric field does positive work on charge plus Q naught in moving it from point A to B. So we have this, okay. So if the right hand side of equation 3 is positive, then the electric field does positive work on charge plus Q naught in order to move it from point A to B. So what conclusion can we draw from this statement? Okay, we need to understand this. So what we find is that, okay, therefore the electric, clear, potential energy decreases, okay, the electric potential energy decreases as the charge plus Q naught is moved from A to B. So we find that potential at A, okay, that is A is at high potential in comparison to B. So VA minus VB, this is positive, clear. So we find this when charge particle plus Q naught, okay, is moving from A to B, it means that it is moving from higher potential to lower potential. So we have this, okay. So let me erase this. So I'm erasing this also, okay. Now we know, but so let me write in this way. We know this, okay? VA minus VB equals integration from A to, okay? So I'm writing in this way. So from B to A, okay? Integration from B to A dV. So we have this. So if we look into the right hand side, the lower limit is B and the upper limit is A. So we are integrating, if we look into this expression, we are integrating from B to A, means we are integrating from lower potential to higher potential. So this is to be noted, okay? So in this expression, so what is dV, okay? So dV, this is small change in potential, okay, due to small displacement, okay, due to small displacement in the path, from B to A. So we have this. Now we can rewrite this expression in this way: VA minus VB equals, on changing the limit, okay, that is lower and upper limit. So we can write integration from A to B dV. So we have this. Clear? So let us call it equation 4. Now we can equate equation 3 and 4, okay? Now from 3 and 4, we can write minus integration from A to B dV equals integration from A to B E, that is electric field, dot displacement. So we have this relation, okay? So let's call it equation 5. So I'm erasing, okay, this. Okay, let me keep this, okay? So we have this. Okay. Now this integral, okay, we can see integral on left hand side equals integral on right hand side, okay? So the above integral is equal for any pairs, okay, of A and B, okay? So for this integral to be equal, okay, for any pair A and B, the integrand must be equal. Therefore, we can write minus dV equals E dot dl. So we have this, okay, and let us call it equation 6. Now let us write electric field in its component form, okay. So we have E equals Ex I cap plus Ey j cap plus Ez k cap, and let us write displacement, okay. We can have displacement of charge plus q naught along x, along y, and along z. So we can write displacement, that is vector dl, equals dx I cap plus dy j cap plus dz k cap, okay. So therefore from 6, okay, we can write minus dv equals electric field is Ex I cap plus Ey j cap plus Ez k cap dot dx I cap plus dy j cap plus dz k cap. So using the dot product of vector, okay, rules, we can write directly right hand side as Ex dx plus Ey dy plus Ez dz. So we have this. Now let's call it equation 7. If the charge plus q naught is displaced along x-axis, okay, then dy equals 0 and dz equals 0. Therefore, from this equation we can write minus dv equals Ex dx, okay. So we have this, clear? Therefore, we can write Ex equals minus dv by dx, okay. So we have this. So we can write this relation in this way also, okay. So here we have y and z as constant. So we have this, okay. So we can write in this way. Now electric field E equals, okay, we know this, Ex I cap plus Ey j cap plus Ez k cap. So we have this, okay. Now in same way, okay, in same way as I wrote in this way, okay, in general V is function of x comma y and z. Therefore we can write Ex equals minus del V by del x, okay. So this is the partial derivative, okay. So it is a partial derivative. So we have this, clear? Next, Ey equals minus del V by del y, and finally Ez equals minus del V by del z. Clear? So we have this. Now let us put these value, okay, ex, ey, and ez in this expression, okay. So what we get? Electric field, that is vector E, equals, so I'm writing in this way, okay, minus, so del V by del x I cap, clear, minus del V by del y, okay, j cap minus del V by del z k cap. So let us do simplification, okay. So I can take minus sign out and we can write in this way, I cap del Vy del x, so z cap del V by del y plus k cap del V by del z. So we can write electric field E equals minus, so I del by del x, okay, this is the partial derivative, plus j cap del by del y plus k cap del by del z, and we have V, okay, outside the bracket. Clear? Now this term, okay, is called del operator. So this is called del or gradient, okay. So this is called del operator or gradient operator, okay. It is, so we have vector sign, okay, over del. So del equals, or del operator equals, I cap del by del x plus j cap del by del y plus k cap del by del z. So as I said earlier, this is the del operator, and it is also called gradient, okay. So we need to note this. So let me erase this. Let us take this, okay. So we can write electric field, that is vector E, equals minus, and we have del operator, okay. So this is del operator, so del V. So we get this, okay, finally. And del V is called potential gradient, okay.